through and like, oh, I guess we should start with the prayer, huh? Okay, I'm sorry. All right, we're going to start with a prayer by Tyler. So if you'll come up.
Our dear Heavenly Father, we're so grateful to be here today as a group of civil engineers and have the opportunity to learn a little bit more about the field that we're getting into. We're grateful, Father, for this opportunity to study here at BYU, to be a part of such a great organization. We pray that Thou mayest bless those who are presenting today, that they'll be able to convey their thoughts to us clearly, and that we will be able to learn from them. And we say these things in the name of Jesus Christ. Amen.
Okay, thank you so much. Okay, so as you can see, we have a whole list of service and other activities going on in October. So for the full list, you can go onto our blog. We will be sending out emails. So just make sure to check your emails, guys, because it's really good to get in your service points and your activity points right now before you get too crazy in the semester. So just get it over with, go do it, go out and serve. It looks really great on your resume as well. And so Concrete Canoe, details coming soon, stay posted, Steel Bridge, Tuesday and Wednesdays at 7, 2:34, you all should go. Steel Bridge is way fun, as well as Concrete Canoe. So get involved in the clubs. All right, BYU ACA polos are finally here. We've been looking at royal blue colors for about a year now. We're finally going to get them. So everyone who wants one, you've got to go onto the blog and click on the link and sign up, put your size so that we can get as many as we need. And be sure to follow all of the social media pages for one free activity point. Okay, and this was up, so I hope you all read it because this is great information to have. If not, I'm sure it will be posted somewhere. Okay, so today we are lucky to have the Electrical Consultants Incorporated here with us. We have Jaron Rave, is that how you say it? Jaron Rave, who is the General Manager in the Salt Lake office. He has been with ECI for 14 and a half years. He is a Master's of Science in Civil Engineering from the University of Utah. And he likes golfing, hiking, mountain biking, volleyball, watching movies, and sports. And as well, we have Nick Barnwell, who is a design engineer who's been with ECI for 3.5 years. He also has his Master's in Science and Civil Engineering from BYU. He likes making spreadsheets, playing guitar, hiking, woodworking, racquetball, and making delicious smoked meats. Okay, in addition, we have Brandon Corbett, who is also a design engineer. He's been with ECI for 3 years. He has his Master of Science in Civil Engineering from BYU. And he likes all things outdoors, spending time with family, professional sports, and fast cars. So please give a warm welcome to everyone from ECI. And the time is now yours.
Thanks, Army. Hello, everyone. So now that you know, we work at Electrical Consultants Incorporated, and I graduated from the University of Utah. I'm guessing probably 2/3 of you have already tuned me out. So let me just address that really quickly. Now, we are civil engineers. We are licensed civil engineers. And so what we do is civil engineering, so we are talking to the right crowd. And then also, I grew up in Orem, Utah. Most of my family went to BYU. I still cheer for BYU. So you guys can trust me. You can listen to me. It's okay. These guys will vouch for me too. I actually am a good guy. Okay. But just to encourage your participation and to make sure that you're paying attention, we are going to be asking a couple of questions during the presentation. And first, people that can raise their hand and correctly answer the question, we've got a small gift for you. So, for everybody, we also have pens down here if you want to take an ECI pen with you on your way out. Go ahead and grab one. So, with that, let's get started. I always enjoy coming and talking to groups of people that are like-minded and understand, as I do, that civil engineering is the greatest profession in all the world, right? I mean, there's just so many things you can do as a civil engineer that are just so exciting and have a big impact on society and really help to improve the quality of life for people all around the world. So I kind of want to just start off and talk about those things. What does a civil engineer do? There are some civil engineers that design structures, right? Places where people can come together to work, to live, to be entertained, to worship, things like that. Those structures can be steel structures, wood structures, made from concrete. They could be entertainment venues. They could be places to go and worship. You know, when I was a civil engineering student, that's when the conference center was being built. And the engineers involved in that project came and talked to us in a seminar just like this. And it was really fascinating to me to talk about all the different loading scenarios that they were considering and talk about the King Truss that they designed to support the roof system, which at the time was the biggest truss of its kind in all the world. So, I mean, just really exciting stuff. There are some civil engineers design bridges, and they tie communities together and make transportation possible and easier. Look at that, isn't that beautiful? Some civil engineers not only tie communities together, but they tie the whole nation together by designing interstates, highways, railways, and airports, making transportation possible. Some civil engineers make life more sustainable in areas, and they make agriculture possible and bring to life recreation by designing dams and reservoirs. Some civil engineers make structures safe and other areas safe by designing foundation systems and retaining walls. And then there's some civil engineers even get into the environmental aspect of civil engineering and make sure that our environment remains safe and clean, that wastewater is disposed of properly, that our rivers and lakes are clean and usable. And so these are just some of the really cool things that a civil engineer can do. And there's a lot more, and as you guys probably already know, that makes civil engineering such a great profession to be a part of. So now I want to ask the question, what does a civil engineer do at ECI? Well, we don't do any of those things. But what we do is we're a part of an industry that is just as important, that also helps to improve the quality of life for people all around the world. We're in the power delivery industry. And even though what we do might not necessarily be considered traditional engineering, the things that we do draw from all of those traditional engineering aspects. We still work with the same kind of materials. We still have the same challenges that other engineers face. We design structures made from steel. Lattice tower structures like this one, they typically will have more different types of members and different types of connections than a standard steel building. And so they seem like they're not very big, but at the same time, they're far more complicated. That is actually a rebar cage for a drilled concrete pier foundation. We design foundations for all of our structures as well. We design wood structures. For any of you that have already had the timber design class and enjoyed the laminated wood part of that design class, we take laminated wood beams and we turn them on their end and call it a pole. We do that. Well, we design concrete structures. We even sometimes get a chance to do fiber reinforced polymer structures. And so we get to do a lot of the same things and use the same materials that other civil engineers do. One of the real challenges that we face is that whereas, if an engineer is designing a building, you get to put a fence around the site and it's a very controlled environment where that structure is going to exist. We design transmission lines that could cross hundreds of miles, and we have to be able to fit them into the environment in which they are. The geography is always a real challenge for us. Here's an example of a line we designed for Rocky Mountain Power that follows the foothills of the Ophir Mountains and goes up and over the Ophir Mountain range. So sometimes we have to design in these terrain that become a real challenge for us. Here's a picture from a site visit that I did in Wisconsin on a project where our client asked us to rebuild an existing transmission line. That line was actually built 70 years ago by mules. The mules brought the poles up, all the materials and the equipment up, and they built that line using mules. stuff. Now today, of course, we're not going to do that. We're going to cut a road in there and use heavy equipment. But it's really fascinating to see how things were done before, how we do it today, and understand the challenges that we face. Because there may be some areas where it's so rough, the terrain is so rough we can't even build a road. And so we have to design our structures to be able to build by helicopter or by some other means. Here's an example of a line that you can see we're designed and built a new line next to this existing one right here, so that you can see the helicopter coming in and flying in a part of the body of that tower and cut right there. So this road, we actually cut this road into the mountain to be able to construct sites here and a few other places on the other side. But some of the places were just not reachable, and so we had to make sure that we designed our structures so that the connections could be possible by helicopter. Okay, so in addition to like mountainous ranges, we also have to, we design our structures for just plain areas for wetlands. Sometimes we have to design them to cross rivers. Sometimes we have to design them to cross lakes. Here's an example of a specialized structure that I got to be a part of the design for that crossed a lake in Oklahoma. And if we have time, we'll talk a little bit more about that later. Here's an example of a structure we had designed to be in a lake. You can see there was one existing, it got damaged, and so we designed a structure to replace it. The bottom part of that structure is actually an open-ended steel tube, and we put a vibration hammer on the top of it and vibrated it down into the ground, attached a steel pole to the top of it. And there's the construction equipment being pushed out on a barge. So in addition to different kinds of geography, we also have to design for different kinds of climates and all the different loading scenarios that come with it. So we have to design our structures to be able to support the loads from, frozen tundra of Canada or other, heavily cold regions. We design our structures for the blazing deserts and the windswept plains of Oklahoma and Kansas, or even Davis County, Utah. That's where I live, in Davis County. And it's funny, I've been there about 12 years, and every 2 years or so, we get this windstorm where the winds are like more than 100 miles an hour. And here's a picture from the last time we had a storm like that, and you can see it blew over trucks, but the power lines in the background, they're still standing. And the civil engineer design goes right. So back in 1984, there was a windstorm. Our vice president actually was working for Utah Power, and he had designed a transmission line out there, and it actually collapsed because the wind got so high. They had a weather station out there that the last reading they got from that weather station was 132 miles an hour wind. And at that point, the weather station blew away, so that's the last reading they got. But that's why the structures, they obviously weren't designed for that high wind. But that's one of the challenges that we get to face is everywhere we go. We might design a line that seems the same as somewhere else, but there's always those unique challenges that we have to design for the different loading scenarios, the different, wherever we are in the country, there's their own challenges. Just a little bit about our company. We're a full-service utility engineering firm, which means we can be involved in projects from start to finish, from conceptual, planning, engineering design, environmental permitting, surveying, construction. We're involved in all of that. We've been organized as ECI since 1985. We have about 500 design professionals and support staff, and one of the largest EPC providers in the country. And we have offices all across the country. As you can see there. So that's us. Bless you. And I'm going to turn the time over to Nick and Brandon. They're going to be talking about some of the projects that they've been involved with since starting their careers at ECI.
Jaron asked me to talk about one of the projects that I've worked on since I've been at ECI. I decided to talk about this project. This is a picture from the construction here. You see them setting the lattice tower with a crane. So this was a 138 kilovolt line, double circuit built with 3 lattice towers. There's just a couple of pictures of just the finished product here. I really like this picture in between the wire phases there. You can kind of see the structure. So I wanted to talk about just one aspect of the design, and that was the foundations that we had to use on these structures. So these foundations right here are what are called grillage foundations. They're a series of steel beams that are placed in the ground, and they're designed to transfer the load from the tower into the soil. And this right here is one of our foundations on what's called a tangent structure. So in the utility industry, a tangent structure supports just the weight of the wire, and then there are dead-end structures. Dead-end structures support the weight and the tension of the wire. And so dead-end structures usually have higher loads on them. So a little bit more of a close-up of that foundation here. Here's one of the foundations for one of our dead-end structures. You can see that it is quite a bit larger. So just to talk a little bit about how a grillage foundation works. So lateral loads are resisted through, these are shear plates in bearing on the grillage base, and then friction from the grillage base against the soil. And then compression and uplift that's transferred in the foundation is resisted through the area of that grillage base bearing on the soil, and then from the weight of the soil above it. So some of the difficult design considerations that we had. So the grillage foundation had to be oriented so that when the leg was connected, the load could be transferred efficiently into the system of beams and bear in the soil. These shear plates had to achieve a certain design depth as well as the base of the grillage. And then this top stub angle, once the grillage foundation was buried, had to be set within some pretty tight tolerances, which I'll talk about a little bit later, so that when they built the rest of the tower on top of that, they didn't have a leg that was 5 feet off and it was already buried 20 feet in the ground. And then at the same time, as they backfilled over the foundation, they had to achieve a certain compaction. And so these were kind of things that we needed to help the contractor know how to achieve our design. So right here you can see a picture after they've buried the foundations, and you can see that they have that one stub angle sticking out, and that it's really important that be set to a pretty tight tolerance. And right here, that's the same structure after they've constructed the last time. So in order to achieve this, we came up with a drawing that we felt like effectively communicated our design to the contractor. I wanted to talk about this today because I feel like in school, this is something that I just didn't learn at all. I mean, all of us are capable of doing calculations that were required to make sure that this foundation was sufficient, but when you get to your job, you're only going to be successful as an engineer if you can actually communicate that design and the contractor can build it. So the manufacturer of the lattice tower actually sent us drawings that had instructions for installation, and we didn't feel like they were sufficient, so we came up with our own. And just zooming in here, you can kind of see this is just an overall view of the lattice tower, and we have dimensions from the center point of the tower, which was given to a survey crew. They went out and they actually staged it. And right here, this was what we call the working point. That was the most important point. The surveyors went out there. Once they did the excavation, the surveyor would get down there, stake that point, and they had to base all of their construction around that point to ensure that once it was buried, it was in the right spot. And up here, we have some of those XYZ coordinates that we calculated out. And here's the tolerances that I was talking about. I just want to read this really quickly. It says, grillage foundations shall be set to a vertical tolerance of 1/8 inch between foundations and a horizontal tolerance of 1/4 inch between foundations or from the tower center stakes. Foundations must be set level such that the stub angles within the above tolerances at stub angle top face. I don't know about you guys, but I don't think I can build Legos to that tolerance. So it was a pretty big challenge, and especially when you've got contractors out there where their only goal is just to get it done. Sometimes they ignore things like this, and so we had to make sure that it wasn't ignored so that there weren't problems. So in order to do this, this is part of the construction phase. You see that there's a protective barrier around here as they're doing this in the excavation. So we had them out there compacting the soil, did this compaction in 12-inch lifts. So when you're burying a foundation 20 feet in the ground and putting 12 inches of soil and compacting, it would take them a full day to do this, and we had 17 miles of line to do this on. We had a geotechnical engineer on site with a densometer, and every time that they did a pass with the compactors, they would get down there and check that it was meeting the compaction that we had specified. And this whole time there was a surveyor on site, and we had given them this point right here that was measuring to make sure that as they compacted it, that was the loop. And it was a pretty involved process. So once they kind of had things set down in the excavation, the process continued, and they just kept the same process going. You can see the geotech down there. So this was definitely one of the funnest projects that I've worked on, and just for reference, I had been working at ECI for probably 6 months when they gave me this project. And so I think that when you get out into your careers, you can expect that your employer is just going to hand you stuff and expect you to be able to do it. And that's actually really exciting. It might seem, kind of nerve-wracking. You might feel like, I don't know that I can do this, but once you get into the design and read up on the methods, you'll find that everything that you learned in school will translate very quickly to that. So, real quick, I just want to make sure that everybody was paying attention. So I've got a question, but I might need some help. I don't know if the ASC officers can help me see who raised their hand first. So, and they're going to look too. So, are you guys ready?
Oh, yeah.
So what were the required vertical and horizontal tolerances for setting the village foundation? Yeah, I think right here.
Quarter inch.
Close. Who's next? I think. Right there.
Yeah. I thought it was a quarter inch and 1/8.
Yeah, that's it. All right. Okay, so we're not, just so we're not messing around. $25 Now everybody's paying attention, right?
Well, I've been at ECI almost as long as Nick. I started about 6 months after he did, and actually called him up after I did my interview, and I said, hey, do you really like this company? Because I think I like them. It's like, yes, it's great. You do really cool projects. So I'm in. And pretty much about the same story as Nick. I came in, did a few months of training, and they handed me a project and said, go. So this is my project that I'm still working on since I started ECI, so it's been about 3 years of design work to do this project. It's in the state of Wisconsin. It's a new 138 kilovolt line going from an existing substation up there in the top left, North Lake Geneva, down to Spring Valley. The reason for this project was there was only one source of power in the Spring Valley, and so they wanted to bring a second source in for reliability. I don't know if you may not have known this, but back in the 70s there was a big power outage in the East Coast, and so it caused a lot of these transmission companies to really try to upgrade all their facilities so they didn't have these blackouts and things like that occurring. As you can see from this picture, this line is built predominantly in a very urban environment. So we have a lot of challenges just dealing with that type of environment. We've got multiple city and county boundaries that all have their own set of regulations that we have to deal with, their own codes and standards. We have a river crossing that we have to deal with. We have a railroad crossing, which can be a big pain. The railroad, for some reason, thinks that electricity is being transferred to the train somehow because, metal rails, it's voodoo, I know. That's what they do. So just a number of challenges that we had to deal with. Before I get into the details of our design, coming out of school, I had very little understanding of what transmission engineering was. So I want to give you just a real quick introduction to transmission design. This, at the top of this structure, this is a basic tangent structure. And like Nick was saying, a tangent structure just simply supports the weight of the conductors. So that's the three top phases of the pole, and then the top is a shield wire. The shield wire is up there for lightning protection, so that your mark doesn't get struck by lightning and then transfer 10,000 extra volts to the society. We don't want that. That would be really bad. In an urban environment, which is this project, the Spring Valley project, you've also got what's called distribution. So the transmission is your highest voltage, 138 kV. So anywhere from 69 kV all the way up to 700 kV. That's 700,000 volts of electricity. Okay, 120 volts per kilo. We're talking 700,000 up there. Okay. Distribution communication. This is the smaller voltage, somewhere between 12 and 39 kV. These are what you normally see on like the typical wood poles next to about every street you drive. A lot of people are like, oh, I didn't notice they were there because they've always been there. It's part of your life. But a lot of times, whenever you're building in an urban environment, state and federal regulations require that they are allowed to attach to your structure, so that we don't have a distribution line on one side of the road and then a transmission line on the other. We end up with picket fences, essentially. We don't want that. So we're required to allow them to attach to our line. So that's one challenge we have to deal with all of their requirements, all of their loadings, and those kind of scenarios. The next thing that we had to deal with was, well, guess what? There's already a bunch of utilities that are buried in the ground. Everyone wants to have, their high-speed Google fiber, so that's buried. We have to have water, gas, sewer, you name it, right? It's already there in the ground, and we have to work around it. Most of the times, they don't want to move. They were there first. They have the priority. It's their right of way, so we have to work with them. And then the next thing that we were dealing with was we're building next to state highways. And if you take some of your transportation classes, you'll learn that there's a thing called the clear zone. The clear zone is a safe distance that any structure has to maintain from the white boundary of a road. So that if in the state of Wisconsin, they get a lot of snow and ice, you lose control of your vehicle, they don't want you to hit a transmission pole on your way off the road. That's bad. That looks bad on us, it's bad for everybody. So we have to maintain that distance. So as you can see, our window of where we want to put a structure is continuously getting smaller and smaller in terms of how we need to get there. So when we began the project, we did a number of site visits. We went out on the line, took a bunch of pictures, hundreds of them. We had to take pictures of every single structure, give it a label, a name, and then we also had to categorize the equipment that was on the existing poles, because the distribution company wants to transfer all of that equipment to our new steel poles. And as you can see, we've got a number of different things to deal with, multiple cross arms, multiple circuits. If you look there on the bottom, so you can see, so these are your distribution right here at the top, and then these three cross arms, that's the distribution. What down here on the bottom, that's what's known as communication cables. So that's your Time Warner cable, Comcast, AT&T. They like to attach those poles as well. So we have to deal with all of them. And to do this, we had to identify a scope for every single structure. So this is just a snippet of one of our pages. We ended up with over 300 transmission poles, over 200 transmission steel poles, and then over 300 distribution wood poles. Because essentially the distribution company is getting a brand new distribution line for free. So of course they want to upgrade all of their facilities, they want to install all new cross arms, put new wire up. I mean, who wouldn't, right? Get a free service. So we had to write out a defined scope for every single structure. What are they going to be doing? Are they installing new cross arms, new equipment? Get that all labeled out. And then come to find out, hey, guess what? The distribution company always deals with wood poles. We're coming in with steel poles. They have no connections for their existing equipment to a steel pole because they like to go out and they just field drill a couple of holes, throw it across our mountain, call it good. But we can't do that on a steel pole that's being fabricated 6 months, in advance of our construction. So we had to develop all these different details for their cross arms, transformers, pin mainstays, you name it, different bangs and brackets. And this coordination is one of the biggest that we had to deal with because we had 2 different distribution companies that we had to coordinate with, and they both wanted different things. So that was a really big effort. It's still ongoing to this day. We've actually issued the first segment for construction. So the poles are sitting in a yard, already fabricated, and the distribution company is asking us, hey, can we do it differently? So the challenge is ongoing. And this was a little snippet of a table that we sent back to the distribution company to identify each of those different weldments and then the spacing in between them, because essentially we needed them to give buy-off before we fabricated all of these poles. Even though, like I said, 6 months later they want to change something. But we try to work with them as best we can. A really big challenge that we had was our underground utilities. So you can see there's a highway off to the right. And we went out on a site visit, we planned one of our structure locations, it's there in Peak. And then we call and locate, so we go and locate, any underground utilities. That's a fiber line in the orange, and then there's a gas line, that's a high pressure gas main. That's a steel 10-inch line, about 400 pounds of pressure. So we have to be a really good safe distance from that. We don't want to impact that at all, that would be bad. Next to a highway, urban environment. We liked this structure, in particular, we thought we were a safe distance away from the road, safe distance away from the fiber and the gas line. We proceed with our design. We come back to the office, get our models, run our numbers. We come back 2 months later, stake the exact same structure location. There's our structure. Holy cow, the gas line has jumped the structure and moved on the roadside, which is a big red flag. And so you can see the before and after of what we're doing. This is only 2 months apart. And what we found out was that there were 2 different locate companies who were locating our gas line. And they both stood by their locates. They said that is definitively where the gas line is. And so we got the gas company involved, and they located it. I don't have pictures of it, but they located it somewhere else, another clear spot. So nobody knew where this gas line was, a very critical artery. And so we ended up having to send out a crew and pothole, which means you'd have to literally dig up the gas line. We did it at every single structure location, and then sent a surveyor out and had them survey that XYZ so we could then bring it back to our office and say definitively we know where the gas line is and where it is not, so we can proceed with our design. So, and this was not the only location where this had happened. Like I said, we had to do it on the entirety of the line just because the unreliability of our locates. The other thing that we were dealing with was, okay, so now the state highways. A lot of times they have plans for the next 10 or 15 years with all their expansion projects. So you have to go to the DOT and say, hey, are you planning on redoing this interchange or this intersection? Are you planning on widening this road later? How is that going to affect our design? This was an intersection where we had planned to put a structure, and luckily the DOT was one of their 30% submittals. They said, yes, we are planning on redoing, we're not expanding, but we are planning on redoing this interchange. Installing some new signal lights and some new traffic lights and those kind of things. So we got their plans, we put our transmission line alignment on it. That's what this, at the bottom left hand corner, that's our transmission line. This is after we have actually moved our structure. So our structure was actually further up north. So we had to move it because of these new lights. They were installing new traffic lights that were taller and had bigger arms on them. And so we have to maintain clearance from our conductor to those traffic light signals we don't want. Say an unqualified worker from the DOT who's changing our lights to accidentally reach over and, touch the transmission. It's also very catastrophic. We don't want that to happen. So we had to increase our structure height. We had to move our alignment, all because of the DOT expansion project. And had we not have gone to the DOT and requested this could have been a major problem in our, if it had been constructed, say, and then we found it after the fact. This was another very, very tight window we had to deal with. There was a dwelling here next to this road, and this road, looks small. This is a state highway in Wisconsin. And because of the distribution line, we were required to overbuild. We had to come in and put our transmission line right away. That's where we would ideally like to put it. The state of Wisconsin will not allow us to build any new transmission line right away over an existing dwelling. Nobody wants the potential of a line falling on their house. That's the safety concern. So we wanted to put it here. Unfortunately, the DOT clear zone says that nothing can be within that yellow area. And so we had to come up with kind of a unique structure type so that we could keep our transmission line sort of over the road, but then also keep the structure outside of that clear zone. What we came up with was a structure like this, where we've got these 9-foot arms to hold the transmission out. These are 9-foot steel arms on one side, and then we've got a 10-foot distribution arm on the back side to hold everything really, really swampus. It looks kind of goofy. I really wish I had a picture of this. It hasn't been constructed yet. The poles are ordered. Construction hasn't taken place. But this keeps our transmission outside of the house, and then also makes us safe in terms of clear zones. It's a very, very difficult challenge. As with any project, you're going to have any number of coordination activities. You've got to deal with the contractor. It's always great to have them involved, get their input on design. Because at the end of the day, the most unique structure isn't the best. The best is what can be easily built. That's what's going to save you the most cost, the most time, and it's going to be better for everybody. You've got all the different regulations you've got to deal with. You've got environmental restrictions. I didn't talk about our river crossing. The river crossing is key because apparently birds migrate all the rivers, I guess. I didn't know that until dealing with these environmental restrictions. So on our river crossing, we had to install bird diverters on our top shield wire so that apparently birds don't fly into the transmission line. I guess that's a thing. I don't know. But it's not my area of expertise. I'm not an environmental guy. You've also got some other issues. These structures can be 1 to 200 feet tall out of the ground. And so if you're near an airport, you've got to deal with height restrictions or maybe special lighting or painting of the structures. And then just even the general public, landowners. A lot of these times we're in front of someone's house. No one wants a big, 4-foot round steel pole in their front yards. We typically don't do that on purpose. We try to put, it has to go somewhere though. So we've got to put it like, maybe a property line between the house or something. But a lot of times even that, they're not really happy with it. And so, we've had to appease some landowners. We bought some trees for some people because we took out some of their trees and they thought that, that was really bad. So we bought some trees, planted some new ones at the same distance. So all these things that, like Nick was saying, you're not going to see it in terms of your engineering classes. But all of these little things, they end up changing your design. And you have to go back and redo all your calculations. And if you don't do this coordination, your project can have some really big problems once you get into construction, or even worse, after it's been constructed. Because then you have to go back and reconstruct and reconstruct it all. So for my question, let's see who was paying attention. I want to know who can tell me the difference between transmission and distribution. Right here.
Transmission is the 7,000 volts that is just for general to put a maybe location. Distribution is just
I like that answer. That's good enough. Okay.
Still got a few minutes before we're going to leave the last 5 minutes for questions from you guys. But I wanted to talk about one fun project that I got to work on when I was designing. Now I just kind of help train these guys to design, and I do quality control checks on their work and keep everything rolling. But when I was designing, I got to be involved in a project in Oklahoma that you can see right here is a power plant. And the project was they wanted to design and build a new line from that power plant and take it to another location about 36 miles to the east. So the problem was there's a lot of constraints here. First of all, there was already 4 extra high voltage transmission lines coming out of that substation and kind of skirting the edge of this lake right here. And the location where we wanted to bring the new line out was to the east of those locations out of that substation. So we were kind of squeezed in against the water already. Additionally, there were a lot of environmentally sensitive areas on the north up here of the lake and on the south, and then some more federally protected lands up here by the rivers over here. So we're like, how are we going to get from here to way over here? And we looked at a lot of different options and found, and with the client, we agreed that we just got to go across the lake. There's just no other way to do it. And that had some problems too, because the closest shoreline was 1.2 miles, was the nearest point shoreline. That's a really long span for a transmission line. The FAA restricted our height to be 200 feet, not be above 200 feet. At the same time, this lake was open for sailboaters, and they have a big mast on their sailboat, right? And we don't want that coming close to the energized conductor. So we had to be at least 50 feet above the water at the high water level, which is a 10-year storm water level. And so we had this box that we had to kind of fit our conductor in. Long span, so our wires are going to sag, but we couldn't have them sag too much. And so what we did was we first came up with a conductor design, a wire design just using stick figures, and luckily there were a couple of islands in the lake that we were able to take advantage of. So our spans, we got them down to about 2,800 feet. And we were able to design a new conductor that is not typically used, that could be tension tight enough so that it would be high enough above the water, and yet our structure still remain under that 200-foot threshold. So we did our wire design, and then we had to design a structure that would be able to accommodate those wires at those high tensions. There's a lot of standard structures. If you guys, after this, you go out and you'll look at some transmission line structures, and you can see that there's a lot of kind of standard structure types. This is one that we were using on the project. We looked at a lot of different options for what are these big structures going to look like, and they were huge. They were just really big, and we thought, you know what, we can do better. We can help our clients save money. We can come up with an alternative design that's really going to be effective. And so we worked with a steel pole manufacturer, and we came up with some plans to design this structure right here, kind of a tripod type design, and actually have a little model of it right here on the table. This is something that's never been designed before, never been used before, and working with the manufacturer for a couple of months, we came up with a design that was going to work, and that's what was actually built. There's some pictures during construction, and you can kind of see, there's some people right there. There's their trucks. So you can kind of see the scale of how big this is. This is 195 feet tall. And you can see the one on the island in the middle of the lake there, and then the one on the other side of the lake there. Really unique design. Saved the client $1.6 million compared to the next effective design that we considered. So they were really happy with this. I mean, that's more than our engineering fee for the project we were able to save our client. And because it was a unique design, I put together a presentation and gave it at an ASCE convention, and they really liked it. And so Transmission Distribution World magazine asked me to write an article about it, and I got to be published with that article based on this project. So kind of a really cool challenge that we faced. We came up with some unique engineering designs and got to be rewarded for it. So that's something that I always encourage you guys. You learn how to be an engineer, and there's always ways to do it. There's traditional ways that we do things, but don't ever forget to think outside of the box. Make sure you keep your creativity. Make sure you are innovative in your designs. And when you have ideas, bring them up and say, hey, I think we could do this better, or we can do something that's a little bit more efficient. Because you guys are the future, and you guys are going to be the ones making this a better place. Okay, that's it. So, any questions? Yeah?
Yeah, one question. Do the solar panels make you, like solar, does that make you nervous at all when you're this or you're not really?
Not really.
Not really.
We work on a lot of solar projects. We've got 3 going on right now. Wind farms, all the new alternative generation will be part of that, bringing that generated power to the grid. Solar is getting better. In the past, not just a few years ago, they were okay, but they're coming up with new technologies, better panels that are more efficient, that are better. Yeah.
So this new design that you talked about to get it high enough above the water, you talked about like being more tension on the wires. How do you deal with the thermal expansion and contraction of the wires? Do you have any problems with that and the wires?
That was all part of the consideration. We were working with a cable manufacturer, and we brought up all of those issues, and we looked at different models, and we found one that would work. We basically had to use annealed aluminum in our design, which normally we don't start that way. Yeah.
You ever work on underground power lines? I know that's some areas that's more common.
Yes, we do.
And what are the advantages of versus?
The advantages of underground is that they're underground. You don't see them, they're not in the way. The problem with underground is they're a lot more expensive. You know, for just a mid-range transmission line, you're talking 20 times more expensive than overhead. If you're talking high voltage, like 345 kV, 50 times. So the cost is just astronomically different. And that's why there's still a lot of overhead because of the cost. The other issue is if there is a problem with it, underground, if something happens, it's really hard to find where the problem is. Where overhead, if something happens, you can find it right away, you can work to get it fixed right away. So maintenance and reliability is actually easier overhead. Yeah.
How much did the wires going over the lake end up sagging?
We maintained our 50-foot clearance. I think we had like 2 or 3 extra feet. We had 25 feet. Our structures were 195 feet. Our conductors were 25 feet below that. Okay, so we're at 170. And then they sagged to about 55 feet above the water. So 115 feet. Did I do the math right? Yeah, go ahead.
So you mentioned like you do a lot of work that needs a lot of technical stuff, like you have roads and you do compaction and stuff. Is that something that you do with sub-consultants, or is that all part of the CI's?
Typically, we use a sub-consultant for roads. We also, one thing we didn't talk about here was the substation side of things, and that's a site also that requires a lot of civil engineering work, and we have our own civil engineers that do that. And some of them also get involved in the roads and the access roads, things like that. But a lot of times we will sub-consult that. A lot of times it's easier to have the contractor be in charge of the roads, and that's typically the way it goes. Just to answer your question though, like I said, we use a specialized conductor on that lake crossing so it wouldn't sag as much. I did another design where we crossed the canyon. It was about the same span length, and that wire was a kind of standard wire that you can order out of the catalog, and that one sagged like about 240 feet. But we were crossing a canyon, so we had 500 feet of room, so we could have it sag a lot. It wasn't a big deal. But for this situation, we needed to limit the sag to 150. Anything else? Okay, thanks everybody for your time. We really appreciate it. If you have any questions, we'll be up here for a while. And again, go ahead and feel free to grab a pen that says ECI on it, and guaranteed it will raise your test score at least 5%.
The pens.